we finally get past section 4.4, and here we are with this cool thing that we call the fundamental theorem of calculus. If that sounds kind of important, it's because it is. So we've kind of seen this before. This thing is our limit definition. And we know that if we apply that to this problem number 1, we'll find out what the exact area is under the curve. But we also know that that would be awful because it would be a pain in our butt, and it's a lot of places for mistakes and all that fun stuff. So then that evolved into this thing over here that we called the definite integral. But the thing about the definite integral is we don't know how to figure it out. Well, this fundamental theorem of calculus is going to finally show us how to figure it out. So here's what you do. Okay? To evaluate a definite integral, this is what happens. The first thing you do is you start with that lowercase f of x. What is the antiderivative of lowercase f of x? Well, that would be capital F of x. Well, then what we're going to do is we're going to take this function, the antiderivative of, we're going to take our antiderivative, and we are going to evaluate it for x equals b and x equals a, and we're going to find the difference between those two things. In other words, we're going to do capital F of b minus capital F of a. And I hope that you recognize that because there's a minus sign in between them, you got to have them in the right order. So you have to put the upper bound in first and the lower bound in second and subtract. You have a question. I bet your question is, where's C? Where is C? What happened to it? Mr. Perkins, we did our antiderivative. Shouldn't I have had a little plus C in there someplace? Well, let's dispel that myth right now. If I would have done a little side work and said capital F of x plus C, and I would have evaluated it from A to B, then I would have had capital F of x, or pardon me, capital F of B plus C minus capital F of A plus C in a quantity. If I clean that up, I end up with capital F of B, and those C's after you distribute it are going to cancel each other out, minus capital F of A. What's the moral of the story? Definite integral, we don't need C. Definite integrals, you don't need C. And why? Because you look at what's in red, all it would do is cancel itself out anyway. So the shortcut is ignore your C, find your antiderivative without C, plug in the upper bound, plug in the lower bound, find the difference, and that difference is going to be your area under the curve. Let's try it a couple times. So problem number 1, first thing I'm going to do, I'm going to find the antiderivative. So what's my antiderivative of 3x squared? Antiderivative of 3x squared would be x cubed. Antiderivative of 2x would be x squared. Antiderivative of 1 would be x. Normally, we would now put a C there. And again, we proved in red over there that you don't, if you do, it's not a big deal. We don't want to put that C in there because it's going to be extra stuff. We're going to evaluate that function from 1 to 4. So we're evaluating it from 1 to 4. Well, we're going to put the 4 in first. So 4 cubed plus 4 squared plus 4 minus 1 cubed plus 1 squared plus 1. So what do we have? 4 cubed is 64. 64 plus 16 plus 4. This is going to be an 84 when we plug the 4 in there, minus 3 when we plug that in there. What's the area under this curve? 81. And we never had to find change in x or right endpoints or any of the rest of that kind of stuff. Fundamental theorem of calculus. We're going to use it a lot. I hope you like it. Problem number 2, find the area of the region bounded by y equals negative x squared plus 3x and y equals 0. Now you're probably having an urge to pull your calculator out. I'm going to tell you that everything we're going to do here is going to be without our calculator. So we need to figure some stuff out. This time we're supposed to find the area of the region. So same deal. What's our region look like? Well, I'm pretty sure that that's a parabola that's opening downward. If I was to find its x-intercepts, I think I'd end up them being at x equals 0 and x equals 3. So I've got a function that crosses the x-axis at 0 and 3. I know it's a parabola. I know it opens down. There's my graph. So I'm trying to find the area of that region. Well, how will I find it? I'm going to use the second fundamental theorem of calculus. I am going to set up a definite integral. My definite integral is going to start at x equals 0 and go to x equals 3. The function I'm integrating is negative x squared plus 3x, and I'm integrating with respect to x. So there you go. Now apply your second fundamental theorem of calculus. Antiderivative of negative x squared. Add 1 to the power. X cubed divided by power, negative 1/3. 3x, add 1 to the power. X squared divided by the power, 3/2. Now into that, we're going to put 0 and 3. Which one do I put in first? It has to be the 3. So I've got negative 1/3 times 3 cubed plus 3/2 times 3 squared minus, if you plug 0 in the first one, you're going to get 0 plus 0. Always plug in your first bound first and your second, your top bound first and your bottom bound second. And I love plugging in zeros. They don't always turn out 0, but they do a lot. 3 cubed is 27 divided by 3 would be 9 with a negative sign on it. Plus 3 squared is 9. 9 times 3 is 27 divided by 2. 9 would be 18/2, and it's negative. So negative 18/2 plus 27/2 says the area under this curve would be 9/2 square units, whatever our units would happen to be. There's our area under our region using the fundamental theorem of calculus.